Thanks for the opportunity to give you an overview of the Low Vision and Blindness Rehabilitation Program. I'm the program director for that. And I want to start with the overview with the NEI funding by program pie chart that you've actually seen across a few councils. This shows the proportion of grants that are funded across our different programs. And if you look at the red piece of pie, you'll notice that the low vision and blindness rehabilitation is very low in calories. In other words, it's the smallest program in the pie. But what I hope to convey to you all this morning is that even if it's small, the value of this program is substantial. So when you read the NEI mission, we know that a big part of the mission is doing everything we can to support research to help prevent and or cure blinding diseases. But the last part of this mission is really crucial, and it's the crux of what the program supports. It's also providing support to understand the special health problems and requirements of the blind. And that's a really, really important charge. The World Health Organization estimates that 285 million people are visually impaired worldwide. So what that means is that 285 million people are living with the costs that visual impairment can inflict. And so when you look at those costs, they're really substantial. There's several activity limitations that the visually impaired endure, reduced mobility just in terms of navigating by foot, but also trying to navigate the buses and metros. I don't have to talk to you all about what it's like to navigate the metro these days, even with intact vision, so you can imagine with that. Difficulty reading is also an important limitation in activity, which is incredibly important when you think about how that can impact your ability to have gainful employment, but also educational opportunities that might be available to you. And there's a number of compromised instrumental activity of daily livings, or ADLs, that the visually impaired have. Whereas cooking may have been a nice, enjoyable hobby, once your vision is impaired, it can become an incredible health hazard. If you can't tell which end of the knife is sharp, or you can't read the display on the oven, you can see that's problematic. So these activity limitations are really crucial when you're thinking about what the rehabilitation needs of this population might be, but also to think about the visual impairment as well. So we know that visual impairment has quite a broad range. It can be absolutely no light detection, total blindness, but it can also include low vision, where you still have some residual usable vision that could be harnessed in order to do some of these tasks, such as reading. We also know that it can differ depending on when the visual impairment occurred. So you may be blind since birth, and you've never known any difference during your life. But it could also be that you progressively lose vision during advanced age. And so the experience that the person has is very different in those two conditions. We also have different etiologies that result in qualitatively different percepts. And again, the rehabilitation needs are going to differ based on what sort of experience the person is having. To the left, this individual might be looking at the boy with a soccer ball. They have macular degeneration, and you notice that what they've lost is their central vision. Those rehabilitation needs might be more related to difficulty reading, whereas the viewer on the right, looking at the boy with the soccer ball, may have late-stage glaucoma. They're losing their peripheral vision, and their issues may be more related to navigation rather than reading. So that's kind of a good setup for the portfolio overview, just as a classification for the different types of grants that I'm going to describe to you. The first set of grants that I'd like to describe are efforts on restoring these ADL functions, trying to offset the limitations that visual impairment can have on a person. The second set of grants that are also included in this portfolio is basic research to understand visual impairment. And that includes behavioral neuroimaging studies. And one of the reasons it's really important is it can inform future rehabilitation efforts. So, to start with those first sets of grants that I mentioned, I'd like to describe the development of a Corobotic Cane. Dr. Kang Yi has been developing this as part of the National Robotics Initiative. That's actually a trans-agency initiative, and we were really happy to see he participated this summer in a Capitol Hill event where Congress wanted to see some of these projects, and Dr. Yi made the front page of the NIH record. To get a sense of what this Corobotic cane is, here's a prototype that he's developed. And the idea is that the blind may use a white cane to navigate around, but we could enhance the capabilities that that cane provides. And so you can see the different components on this prototype. It uses computer vision that can identify not only obstacles, but also identify what they are. So it would be important for the cane user to know if there's a set of stairs ahead versus a door. It also can communicate that information back through a Bluetooth headset. So the user can get auditory information about what these objects are in front, but also he's developing the capability for pathfinding with this robot, and that information can be relayed back to the user through tactile and steering maneuvers, indicating to the person whether they're going to go left or right. So you can imagine if they are navigating a building, they could download the map of the building, and the cane could actually tell them which way to go. Another technology that's been harnessed quite successfully for the visually impaired are developing smartphone-based computer vision applications. A couple of years ago, the New York Times had an article that was about the fact that the visually impaired have really embraced smartphones as a technology in order to relieve some of the issues they have with ADL functions. James Coughlin at Smith Kettlewell has a background in computer vision science and has decided to really channel it to trying to address the needs of the blind by extracting visual information from messy natural environments and developing apps that people can download onto their phone. So one example here is the smartphone Crosswatch app. And it addresses a really crucial issue for many visually impaired, and that is trying to get across busy intersections. The way the smartphone Crosswatch app works is that the user can aim the camera towards the walk light. It can then identify whether the walk light is saying go or stop. It can help them attain alignment in the crosswalk, which is actually very, very difficult, especially for the blind. Cane users can use them when there's a curb to knock against, but when you're in a crosswalk, even with the zebra stripes, they're not doing you much good. So the app can actually tell the person whether they're maintaining alignment as they're crossing the street. It can also monitor vehicles and communicate that back to the person. And very generally, the way this app works, it has two main components. One is a geographic image system where Dr. Coughlin and colleagues have taken satellite imagery. You can get imagery from street views and even crowdsourcing to develop this knowledge base for the system to use. It contains a lot of information about the geometry of each of these intersections. And then it combines a camera and built-in sensors so that in real time, the user can get this information while crossing the street. Another smartphone app that Dr. Coughlin has been developing is a display reader. This is actually for appliance displays. They're an increasing array. They're everywhere. We can't even find a dryer that uses dials anymore. They all have these electronic displays. But they are very difficult to read. They're difficult for me to read, but if you have low vision, they tend to have very low contrast. The digits use unusual formats, and you can also have issues with glare. And so the way this app works is you're able to hold up the camera to the image. It'll acquire that image and translate it either by enhancing it to up the contrast, to change the format of the font, but can also read aloud to the user. And the important aspect of this is it's going to make appliances accessible to people who can't read the screens. And so I have a microwave here, a thermostat here, but this bottom device, this is a glucose meter. There are a number of people with diabetes who can't read the readout. So if they had this app, they would be able to monitor their health needs better. And I've also put up here open source code to remind me to mention that one of the things that Dr. Coughlin does is make this source code available for download for free, anyone who goes onto his website. Okay, another example of assistive devices that have been developed for the visually impaired comes from Dr. Ellie Pelly at Scapins. He received an NEI Bioengineering Research Partnership Grant, which is really to team very, very interdisciplinary expertise, in this case engineering and low vision expertise, to develop something to help patients with hemianopia navigate. Hemianopia is a condition where you lose half the visual field, generally to one side of the vertical midline. And one of the problems that these patients really talk about is the difficulty in navigating. They're worried about bumping into people and obstacles. And so what Dr. Pelly has created are these visual field expansion devices by using expansion prisms installed in the lens of regular eyeglasses. What the prism does is it directs images from that blind spot into the functioning visual field. And after some time of adapting to this different experience, it can actually expand the field of view for patients up to about 20 degrees. Another example of a successful bioengineering research partnership project was that of Gordon Legg. He had a very different interdisciplinary team. He included low vision expertise, computational modeling, and the engineers were those who were involved in buildings, lighting and design of buildings. And what he wants to get at is the issue of visual accessibility of indoor spaces. He's talked about the notion that we have environmental modifications for individuals in wheelchairs. So now when you go into a building, you generally see wheelchair ramps in most of these buildings. He wanted to identify the features that are difficult for the visually impaired and use those included in a computational model to develop and deploy an open source software modules that architects and designers can use when they're designing buildings. And so just to give you an example of the type of data that Dr. Legg has been using, here's some image variations, one single shot, 4 different times in the morning. And you can see there's ambient lighting that comes through the windows, but it changes the look of the different obstacles that are in view. Now, with intact vision, this is pretty easy to handle. But when they used a low acuity simulation to blur those exact same images, now what you can see is all of the 3D information is gone. It's very difficult to discern what's a stairway and what's a piece of carpet. So you could imagine if you're a low vision person entering this building for the first time, you might not have any idea that that stairway exists. Okay, so those are the projects that I wanted to highlight on restoring ADL functions. But I also mentioned that we support basic research to understand visual impairment. So let me just run through a few of those projects. Shireen Hassan at Indiana University has a behavioral project where she's looking at risky street crossing situations for visually impaired pedestrians. She uses an outdoor laboratory research that has real traffic scenarios. And what she wants to look at is the type of wayfinding behaviors and cues they use, and to see if we can use this to evaluate ways to mitigate street crossing risk. So just very briefly, I want to give you a sense of one of her experiments. She has the pedestrian waiting to cross the road here, and what they evaluate their crossing time so that they get a baseline crossing time for each of the subjects. And then what the person is told to do is, okay, you're looking straight ahead. Now you get a signal. I want you to look. You'll see a car coming. And then you'll get another prompt, and you have to say whether or not you're going to cross the road. And what's varied is the gap time between where the car is and when they would cross the marker where the person would cross. So some of them are long, and some of them are short. And so I know this is a very busy slide, but what I want to do is direct your attention to that yellow line at the margin category and go left. That's the danger zone. That's where people are saying, yes, I would cross, but that gap time from where the car was and that crossing period is actually shorter than what that person needed to cross the road. And what is impressive to me about these data is they were broken down by the type of visual impairment they have. And so we have visual acuity loss, visual field loss, and the dots in green are those who have combined acuity and field loss. In other words, their vision is worse than the other two groups. But what you can see in that danger zone is that more of those individuals are making yes decisions to cross the street. That's counterintuitive. You would think that if your vision is worse, you would be more conservative. But what they're finding is that they're actually less conservative. Okay, I think most people here are familiar with the human connectome. We're going now into the brain. This is a trans NIH project that began in 2009 with the idea of trying to map the wiring diagram of the entire living human brain. There were two main projects. They've been acquiring and sharing connectivity data with a total of 1,200 healthy adults. I'd also point out that the other amazing thing that the human connectome accomplished is the fact that a rock band used this image for their album cover. I think that's a first. And now they've expanded the connectome to invite people who can bring in disease patients to the connectome. So the connectome in human disease. And NEI is actually funding two of these projects. Christina Vischer from the University of Alabama, Birmingham, has a project where she is going to be using the HCP protocols to scan individuals with macular degeneration, 50 patients and 50 age-matched controls. And so what's really important here is these data will be publicly available for people to use, but also there are opportunities for her to pursue scientific questions, in particular whether the visual cortical connectivity changes following central visual field loss. And the second Connectome project that we're funding is that of Bosco Tian from USC and Jeff Aguirre at Penn. They are looking at collecting a database of retinal and central visual pathway data for 6 retinal disease types. So they're actually aiming for 260 different patients and controls, and also to develop new analysis tools to co-register the ophthalmic and neural measures. So in other words, they will be getting very high resolution OCTs for all of these patients. And what they hope to be able to do is map those measures onto the optic radiation measures as well as cortical fMRI measures. One of the interesting points just to bring up, I had it on the slide to remind me, so they're not just looking at these patient data to see how that changes as a result of their impairment, but also they have some patients that will be getting a treatment. And so with those patients, they'll be looking at pre and post-treatment data to see if we can see changes in the brain that are reversible. And the last project to highlight for you that's supported in this project, in this program, is Pavan Sinha from MIT Project Prakash. This is a unique program that melds humanitarian needs and scientific quests together. NEI has been supporting the scientific quests. So the humanitarian needs. Well, nearly 60% of all childhood blindness in the developing world is either preventable or treatable. The two examples that I have pictured up here are corneal opacities and congenital cataracts. Now, if a child is born with one of these conditions in the United States, they would receive surgery for that within weeks of their birth. But in rural India, that's not the case because of poor access to medical care. So what Dr. Sinha has done in collaboration with the Shroff Charity Eye Hospital is gone out to these rural areas, done screenings to find children who are good candidates for surgical treatment. They bring them in, do the surgery, and then the scientific quest can begin. Now we have a population of children who've been severely impaired since birth. And at different points in their lives, they've received surgical treatment, and we can see how their vision develops after that treatment. Now, the picture that I've put up here is one that I would venture to guess that most people looking at that actually see two squares, almost a three-dimensional picture with one square overlaid on the other. But that's actually a learned percept. It's difficult. So here's an example of one of the patients, SK, who was asked to trace these different objects. And you can see with the superimposed squares, he doesn't see two squares. He just over-fragmentizes. All he can see are the different lines. And it's not just with these geometrical objects. You can also see it when he's looking at real objects and asked to trace those. And so I think I have time that I can play this short video. What you'll see here is that SK, let's see if it's going to work. No, sorry, but I can describe. When SK sees this image of the triangle in visual noise, he doesn't see the triangle. He can't identify it. He says, I can't make it out. But when that triangle is put in motion and is moving around the screen, then he says, I see the triangle. If you give him the two superimposed squares, he doesn't see the two superimposed squares. But when you move one of them, those features bind, and then he says, I see these two different squares. What's really impressive is that 18 months later, when he comes into the lab, he's now able to see this triangle in the noise. In other words, he's developed that ability to parse out objects. Okay, so a bit of summary after this whirlwind overview. I talked about the activity limitations that individuals with visual impairment have, but I've added in yellow some of the projects that NEI is supporting to try to ameliorate some of those issues, mobility, reading, and different activities of daily living. But I'd also like to leave you with this. The notion of activity limitations could also be shattered. And I don't know how many of you had the opportunity to see some of the Paralympic competitions this summer. But boy, these people were shattering the notion that they have any limitations. All of these images are blind athletes who were playing one heck of a game of soccer, or football for some of you. This woman in the middle running has not only qualified for the Paralympics Boston Marathon, but she was also qualified for the Paralympics in Rio by running a 1,500 in 4 minutes and 57 seconds. And the Washington Post did a great review of this swimmer who lost his eyes because of an exploding IED device. All they need are a few additions of either help, but they can shatter these limitations. Thank you.